Copper is a chemical element with symbol Cu and atomic number 29. It is a soft, malleable and ductile metal with very high thermal and electrical conductivity. A freshly exposed surface of pure copper has a reddish-orange color. It is used as a conductor of heat and electricity, as a building material, and is a constituent of various metal alloys. Copper is found as a pure metal in nature, and this was the source of the first metal to be used by humans. California, 8000 BC, it was the first metal to be smelted from its ore. California, 5000 BC, it was the first metal to be cast into a shape in a mold. California, 4000 BC, and it was the first metal to be purposefully alloyed with another metal, tin, to create bronze. California, 3500. In the Roman era, copper was principally mined on Cyprus, the origin of the name of the metal from Aes Ypres, later corrupted to Uprum, from which the words copper, cuivre, copper and kupfer are all derived. Its compounds are commonly encountered as copper salts, which often impart blue or green colors to minerals such as azurite, malachite and turquoise, and have been widely used historically as pigments. Architectural structures built with copper corrode to give green verdigris. Decorative art prominently features copper, both by itself and in the form of pigments. Copper is essential to all living organisms as a trace dietary mineral because it is a key constituent of the respiratory enzyme complex cytochrome C oxidase. In mollusks and crustacea, copper is a constituent of the blood pigment hemocyanin, which is replaced by the iron complex hemoglobin in fish and other vertebrates. The main areas where copper is found in humans are liver, muscle and bone. Copper compounds are used as bacteriostatic substances, fungicides, and wood preservatives. Characteristics: physical copper, silver and gold are in group 11 of the periodic table, and they share certain attributes. They have one s orbital electron on top of a filled d electron shell and are characterized by high ductility and electrical conductivity. The filled d shells in these elements do not contribute much to the interatomic interactions, which are dominated by the s electrons through metallic bonds. Unlike metals with incomplete d shells, metallic bonds in copper are lacking a covalent character and are relatively weak. This explains the low hardness and high ductility of single crystals of copper. At the macroscopic scale, introduction of extended defects to the crystal lattice, such as grain boundaries, hinders flow of the material under applied stress, thereby increasing its hardness. For this reason, copper is usually supplied in a fine-grained polycrystalline form, which has greater strength than monocrystalline forms. The softness of copper partly explains its high electrical conductivity and thus also high thermal conductivity, which are the second highest among pure metals at room temperature. This is because the resistivity to electron transport in metals at room temperature mostly originates from scattering of electrons on thermal vibrations of the lattice, which are relatively weak for a soft metal. The maximum permissible current density of copper in open air is approximately 3.1 times 106 A per square meter of cross-sectional area, above which it begins to heat excessively. As with other metals, if copper is placed against another metal, galvanic corrosion will occur. Together with cesium and gold, and osmium, copper is one of only 4 elemental metals with a natural color other than gray or silver. Pure copper is orange-red and acquires a reddish tarnish when exposed to air. The characteristic color of copper results from the electronic transitions between the filled 3d and half-empty 4s atomic shells. The energy difference between these shells is such that it corresponds to orange light. The same mechanism accounts for the yellow color of gold and cesium. Chemical copper does not react with water, but it does slowly react with atmospheric oxygen to form a layer of brown-black copper oxide which, Unlike the rust which forms when iron is exposed to moist air, protects the underlying copper from more extensive corrosion. A green layer of verdigris can often be seen on old copper constructions such as the Statue of Liberty. Copper tarnishes when exposed to sulfides, which react with it to form various copper sulfides. Isotopes. There are 29 isotopes of copper. 63 Cu and 65 Cu are stable, with 63 Cu comprising approximately 69% of naturally occurring copper. They both have a spin of 3 halves. The other isotopes are radioactive, with the most stable being 67 Cu with a half-life of 61.83 hours. 7 metastable isotopes have been characterized, with 68 MCU the longest-lived with a half-life of 3.8 minutes. Isotopes with a mass number above 64 decay by beta-, whereas those with a mass number below 64 decay by beta+. 64 Cu, which has a half-life of 12.7 hours, decays both ways. 62 Cu and 64 Cu have significant applications. 62 Cu is used in 62 Cu PTSM, that is a radioactive tracer for positron emission tomography. Occurrence copper is synthesized in massive stars and is present in the Earth's crust at a concentration of about 50 parts per million, where it occurs as native copper or in minerals such as the copper sulfides chalcopyrite and chalcocite, the copper carbonates azurite and malachite, and the copper oxide mineral cuprite. The largest mass of elemental copper discovered weighed 420 tons and was found in 1857 on the Quinault Peninsula in Michigan, U.S. Native copper is a polycrystal, with the largest described single crystal measuring 4.4 times 3.2 times 3.2 centimeters. Production. Most copper is mined or extracted as copper sulfides from large open-pit mines in porphyry copper deposits that contain 0.4 to 1.0% copper. Examples include Chuquicamata in Chile, Bingham Canyon Mine in Utah, United States, and El Chino Mine in New Mexico, United States. According to the British Geological Survey, in 2005, Chile was the top mine producer of copper with at least one-third world share, followed by the United States, Indonesia and Peru. Copper can also be recovered through the in-situ leach process. Several sites in the state of Arizona are considered prime candidates for this method. The amount of copper in use is increasing and the quantity available is barely sufficient to allow all countries to reach developed world levels of usage. Reserves. Copper has been in use at least 10,000 years, but more than 95% of all copper ever mined and smelted has been extracted since 1900, and more than half was extracted in only the last 24 years. As with many natural resources, the total amount of copper on Earth is vast. However, only a tiny fraction of these reserves is economically viable, given present-day prices and technologies. Various estimates of existing copper reserves available for mining vary from 25 years to 60 years, depending on core assumptions such as the growth rate. Recycling is a major source of copper in the modern world. Because of these and other factors, the future of copper production and supply is the subject of much debate, including the concept of peak copper, analogous to peak oil. The price of copper has historically been unstable, and it sextupled from the 60-year low of 60 cents per pound in June 1999 to $3.75 per pound in May 2006. It dropped to $2.40 per pound in February 2007, then rebounded to $3.50 per pound in April 2007, better source needed, in February 2009. Weakening global demand and a steep fall in commodity prices since the previous year's highs left copper prices at $1.51 per pound. Methods. The concentration of copper in ores averages only 0.6%, and most commercial ores are sulfides, especially chalcopyrite and to a lesser extent chalcocite. These minerals are concentrated from crushed ores to the level of 10 to 15% copper by froth flotation or bioleaching. Heating this material with silica in flash smelting removes much of the iron or slag. The process exploits the greater ease of converting iron sulfides into its oxides, which in turn react with the silica to form the silicate slag, which floats on top of the heated mass. The resulting copper matte consisting of Cu2S is then roasted to convert all sulfides into oxides. 2Cu2S plus 3O2 2Cu2O plus 2SO2. The cuprous oxide is converted to blister copper upon heating. 2Cu2O4 Cu plus O2. The Sudbury matte process converted only half the sulfide to oxide and then used this oxide to remove the rest of the sulfur as oxide. It was then electrolytically refined and the anode mud exploited for the platinum and gold it contained. This step exploits the relatively easy reduction of copper oxides to copper metal. Natural gas is blown across the blister to remove most of the remaining oxygen and electro-refining is performed on the resulting material to produce pure copper. Cu2++, 2E- Cu. Recycling. Like aluminium, copper is 100% recyclable without any loss of quality, regardless of whether it is in a raw state or contained in a manufactured product. In volume, copper is the third most recycled metal after iron and aluminium. It is estimated that 80% of the copper ever mined is still in use today. According to the International Resource Panel's Metal Stocks in Society report, the global per capita stock of copper in use in society is 35 to 55 kg. Much of this is in more developed countries rather than less developed countries. The process of recycling copper is roughly the same as is used to extract copper but requires fewer steps. High-purity scrap copper is melted in a furnace and then reduced and cast into billets and ingots. Lower-purity scrap is refined by electroplating in a bath of sulfuric acid. Alloys. Numerous copper alloys exist, many with important uses. Brass is an alloy of copper and zinc. Bronze usually refers to copper-tin alloys, but can refer to any alloy of copper such as aluminium bronze. Copper is one of the most important constituents of carat silver and gold alloys, and carat solders are used in the jewelry industry, modifying the color, hardness and melting point of the resulting alloys. The alloy of copper and nickel, called cupro-nickel, is used in low-denomination coins, often for the outer cladding. The US 5-cent coin called a nickel consists of 75% copper and 25% nickel and has a homogeneous composition. The alloy consisting of 90% copper and 10% nickel is remarkable for its resistance to corrosion and is used in various parts that are exposed to seawater. Alloys of copper with aluminium have a pleasant golden color and are used in decorations. Some lead-free solders consist of tin alloyed with a small proportion of copper and other metals. Compounds. Copper forms a rich variety of compounds, usually with oxidation states +1 and +2, which are often called cuprous and cupric, respectively. Binary compounds. As with other elements, the simplest compounds of copper are binary compounds, i.e., those containing only two elements. The principal ones are the oxides, sulfides, and halides. Both cuprous and cupric oxides are known. Among the numerous copper sulfides, important examples include copper sulfide and copper sulfide. The cuprous halides with chlorine, bromine, and iodine are known, as are the cupric halides with fluorine, chlorine, and bromine. Attempts to prepare copper iodide give cuprous iodide and iodine. 2Cu2++, 4I-2 plus I2 coordination. Chemistry. Copper, like all metals, forms coordination complexes with ligands. In aqueous solution, copper exists as Cu6 2+. This complex exhibits the fastest water exchange rate for any transition metal-aquo complex. Adding aqueous sodium hydroxide causes the precipitation of light blue solid copper hydroxide. A simplified equation is Cu2++, 2O- aqueous ammonia results in the same precipitate. Upon adding excess ammonia, the precipitate dissolves, forming tetraaminer copper. Cu42 plus 4NH3, Cu24, 2 plus 2H2O plus 2O minus. Many other oxyanions form complexes. These include copper acetate, copper nitrate, and copper carbonate. Copper sulfate forms a blue crystalline pentahydrate, which is the most familiar copper compound in the laboratory. It is used in a fungicide called the Bordeaux mixture. Polyols, compounds containing more than one alcohol functional group, generally interact with cupric salts. For example, copper salts are used to test for reducing sugars. Specifically, using Benedict's reagent and Fehling's solution, the presence of the sugar is signaled by a color change from blue Cu to reddish copper oxide. Schweizer's reagent and related complexes with ethylene diamine and other amines dissolve cellulose. Amino acids form very stable chelate complexes with copper. Many wet chemical tests for copper ions exist, one involving potassium ferrocyanide, which gives a brown precipitate with copper salts. Organocopper chemistry. Compounds that contain a carbon-copper bond are known as organocopper compounds. They are very reactive towards oxygen to form copper oxide and have many uses in chemistry. They are synthesized by treating copper compounds with Grignard reagents, terminal alkanes or organolithium reagents. In particular, the last reaction described produces a Gilman reagent. These can undergo substitution with alkyl halides to form coupling products. As such, they are important in the field of organic synthesis. Copper acetylide is highly shock-sensitive but is an intermediate in reactions such as the Kadiot-Chodkovich coupling and the Sonogashira coupling. Conjugate addition to N1s and carbocupration of alkanes can also be achieved with organocopper compounds. Copper forms a variety of weak complexes with alkenes and carbon monoxide, especially in the presence of amine ligands. Copper and copper is most characteristically found in oxides. A simple example is potassium cuprate, KCuO2, a blue-black solid. The best-studied copper compounds are the cuprate superconductors. Yttrium-barium copper oxide consists of both Cu and Cu centers. Like oxide, fluoride is a highly basic anion and is known to stabilize metal ions in high oxidation states. Indeed, both copper and even copper fluorides are known, K3CuF6 and Cs2CuF6, respectively. Some copper proteins form oxocomplexes, which also feature copper. With tetrapeptides, purple-colored copper complexes are stabilized by the deprotonated amide ligands. Complexes of copper are also observed as intermediates in reactions of organocopper compounds.